So, hello all. I'm Gitanjali. I'm a PhD scholar from IIT Delhi. I welcome you to this live section of the course Quantum Mechanics 1. I hope uh, in the last section we have primarily talked about the spin angular momentum, which is confirmed by the Stern-Galerk experiment. So now in this live section, we will talk about one additional. We will talk about the problem where when the particle have both spin angular momentum as well as the orbital angular momentum. So without further delay, so let's start the section. So I hope the screen is visible. Yes. So is my voice audible? Okay, so let's start the section. So, so this is the first problem, which is related to the orbital angular momentum. So let me read out the question for you. So the question is, consider a spinous particle with orbital angular momentum L equal to 1. The Hamiltonian of the particle is H is A Lx Ly plus Ly Lx plus B Lz square. So particle is spinless. So that means S is 0. And it is given the Hamiltonian of the particle is this. So now it is asking about the commutator of the Hamiltonian with the Z component of the angular momentum is. So it is based on the commutation relation H. So it is asking about what will be the commutation relation of Hamiltonian with the Z component of orbital angular momentum. So this question is simple. You can easily solve it using the properties of the commutation relation and some of the commutation relation of orbital angular momentum. So, so Hamiltonian is this, and there is LZ operator. So now what you can do is just use the properties of commutation relation. It will be LXLY. So based on the commutation relation, the plus part will get splitted into individual part. We'll get commutation relation of first with second, second with second, and third with second. This will be LZ plus A times Ly Lx Lz plus B times Lz square Lz. So the last term is 0, because Lz commutes with Lz. Now for the first and second term, what you can do is you can again use the properties of commutation relation, like if ABC, you want to find out the commutation relation of ABC, then what you can do is equivalent to ACB plus ABC. So use this. So if you use it, then this first term will become Lx Lz Ly plus Lx, Ly, Lz. This is the first term plus, let me erase this one, plus A times. The second term, you can also use the property of commutation relation. It will become Ly, commutation relation of Lx with Lz, plus Ly, Lz commutation relation with Lx. This Lx Ly commutation relation, you already know it is minus IH cut Ly. And this one, IH cut Lx. This is also minus IH cut Ly. And this one is IH cut Lx. So now the total expression will become A. So these two terms are same. So it will become minus 2IH cut Ly square plus 2IH cut Lx square. So now you got 2IH cut A Lx square minus Ly square. So this will be the commutation relation for the Hamiltonian with the z component of orbital angular momentum. Okay. You have any query, Ankit?
I have a question.
Tell me.
First of all, good evening, ma'am. I'm in this
Good
question.
evening.
You have. I'm just a minute. Can you scroll up to a little bit?
Is it
Yes,
fine?
ma'am. Yes, ma'am. Ma'am, in this you have done that. You have taken the A common from the both of the terms, and then you have added the minus I cat Ly. So it should be minus 2I cat Ly, not Ly square. Why have you done Ly square? Because you are adding this.
Wait. So there is a Ly here also. So I will highlight that there is a Ly here, right?
So you are multiplying I cat Ly and Ly. These terms. Okay. Okay.
So that's why you got Ly square.
Okay, ma'am.
Okay. So this will be the answer. 2I cut Lx square minus Ly square. So answer will be B. So it's the simplest question. You just need to recall the properties of commutation relation as well as the what is the relation for orbital angular momentum. If you know that, then you can easily find out what will be the commutation relation of the expression which is asked in the question. So let us go to the second question. So the second question is, suppose the measurement of Sx was found to be minus h cut by 2, and immediately after the measurement, we measured the Sz component of spin angular momentum. Then the possible results of measuring Sz are. So it is based on Stern-Gerlach experiment. So in Stern-Gerlach experiment, what we see that the spin angular momentum gets split into two parts. For spin up particle, for spin 1, it will be 3. So according to the spin, you will get a different number of spots in the screen. So now what has been done in this experiment is they measured the Sx first and they found that the result is minus h squared by 2. Now immediately after the measurement, we measured the z component of the spin. So after that, we measure z component. So now it is asking about what are the values we will got here after measuring Sz. So it's the conceptual question. So you know that this Sx and Sz, they are incompatible operator. So Sx Sz commutation relation is not equal to 0. So that means they are incompatible observables. So if immediately if you measure Sx and you got minus h cot by 2, so after that if you measure z component, then you will get both plus h cot by 2 and minus h cot by 2 because they are not compatible. So you cannot express one in terms of the eigenvalues of the other. That is why you will get both spin if you measure the z component. So the answer will be plus or minus h cot by 2. So similarly, if you measure y component also, you will get the same answer. So you will get plus or minus h cot by 2 if you measure y, sy. But if you immediately after the experiment, if you measure Sx also, means instead of sy instead you measure Sx, then you will get minus h cot by 2 only with 100% probability, right? So here the probability will be 50-50. But if you measure Sx, then you will get minus h cot by 2 with 100% probability. So it's based on this Stone-Garlock experiment. So now let us see the third problem. So the third one is consider an operator O equal to half jy plus jy. Then the expectation value of this operator is. So it is based on the expectation value of a operator. So what you have to do, you have to use the raising and lowering operator concept. So Jx and Jy eigenvalue you will get from the raising and lowering operator. So first what you have to do, you have to express Jx and Jy, the whole operator O, in terms of the raising and lowering operator. So Jx, you know, it is half J plus J minus, and Jy it is 1 by 2y J plus minus J minus. So now let us express both the terms Jx Jy and Jy Jx in terms of J plus and J minus. So Jx Jy we will got 1 by 4i J plus J minus. This one is J plus minus J minus. So you know that these J plus and J minus are not compatible operators. So you have to multiply term by term. So you will get J minus square plus J minus J plus minus J plus J minus. And this is nothing but the minus of commutation relation of J plus with J minus. This whole term. So the final one would be J plus square minus J minus square minus commutation relation of J plus with J minus. So this one, you know, it is nothing but 2h cot Jz, right? So the final expression would be 1 by 4i J plus square J minus square minus 2h cot Jz. So this is the expression for the first term, this one. Now let's see the second term. So second term is jy with jx. So you will get 1 by 4i j plus minus j minus with j plus with j minus. So this expression, if you work it out, similar to the first term, you will get j plus square minus j minus square, and instead of minus 2h cos jz, here you will get 2h cos jz. So now the operator would be half jx jy plus jy jx. So this means you will get 1 by 4i. This term will cancel when you add the first and second term. So the term that will remain is j plus square minus j minus square. So this is how you can represent the operator in terms of raising and lowering operator. Now, if you want to find out the expectation value, so the expectation, if you take Jm is the eigenstate, then the expectation value would be 1 by 4i Jm j plus square minus j minus square with Jm. So you will get two terms, Jm j plus square Jm minus j minus square j. Now let's see the first term, this one. So when j plus act on jm, so it will raise the state of the system, it will raise m to m plus 1. So if you act j plus twice on jm, then you will get a state which is eigenstate j and m plus 2. Right? Now if you take the inner product of this one with jm here, then you will get 0 because the state is changed after when j plus act on this one, the state gets changed, so the inner product would be 0. Similarly, when j minus acts on this jm, it will changes the state of the system. So if j minus acts twice on jm, then you will get a state j and m minus 2. Now, if you take the inner product of jm minus 2 with jm, then you will get 0. So that means the expectation value is 0. Right? So whenever you are seeing j plus and j minus and they are asking about the expectation value, then in that case, the expectation would be 0 because the state gets changed when j plus and j minus acts on the state. So that means the expectation value of this operator is 0. So this is the answer for this question. So these are some of the simple problems. We slowly move towards the
Excuse me, ma'am.
Tell.
Ma'am, the questions you are now solving, where can I find these problems? Or in which book?
So you can refer to Jetli. Jetli, quantum mechanics concept and application. So there are
Yes, ma'am, not in Jetli.
So there are a lot of problems in that book. So you can.
These problems are from that specific book, Jetli.
No, it's not like all the problems are from the same book. There are from Griffith, they are from Jetli. So some of the problems are from internet. So you just have to solve many problems so that you can understand the concept better. So it's not like you got stick to one book only. For concept, you can stick to one book, but for problems, I would suggest uh, look for many books like Griffith, Jetli, Sakurai, and internet also. You can type the problems based on quantum mechanics. You can just write uh, in internet key you want to uh, solve some problems, let's say on harmonic oscillator. So you just search on the internet, so you will get some problems.
Okay. So, and for theory part, which book should I refer to for theory?
Theory part you can read from Jetli. So it's clearly mentioned there, each concept with problems. So just stick to that book. Don't read many books for concept. Just stick to one book.
Okay.
So I think that is better if you want to understand the concept.
Okay. Thank you.
So let us move to the next question. So for problem solving, the concepts should be clear in your mind because in that way you can easily solve a problem. So the main is the concept and you have to remember some of the basic properties. So let us, okay. Fourth question is the expectation value of SZ minus H cut SZ plus H cut of a spin 1 particle in the state Sm is non-zero for any m. So it is asking about, so it is telling the expectation of this operator is non-zero for any m. So whether this statement is true or not. And the particle is spin 1 particle. So let us see whether this statement is correct or not. So the expectation is nothing but Sm Sz minus H cut Sz Sz plus H cut with Sm. Now you know that Sz when it acts on Sm, it will give MH cut Sm. So that means, so let me write here. So when Sz acts on Sm, it will give MH cut Sm. So that means when Sz plus H cut acts on Sm, it will give M plus 1 H cut Sm. It's a constant. H cut is a constant, so the state will remain change and you will get M plus 1 H cut. And when Sz minus H cut when it acts on Sm, we'll get M minus 1 H cut Sm. So now let us see the expectation value. Sm Z minus H cut Sz Z plus H cut Sm. So first, this operator will act on Sm. You will get M plus 1 H cut Sm. Then the Sz will act on it. Let me write the final. So you will get M plus 1. Now Sz will act on Sm. So you will get MH cot. So there are two constant now. Now in the final step, this last operator will act on Sm. Then you got M minus 1 H cot Sm. Right? Now it is given the particle is spin 1 particle. So that means the M value would be 1, 0, minus 1. Now if you put 1, 0, minus 1 here, for let's say for 0, you will get 0 because M is here. For 1, there is M minus 1 term, so you will get 0. For minus 1, you will get, there is a M plus 1 term here, so you will get 0. So for all the values of M, the expectation value is 0. So that means this statement is not true. It's false. So the answer will be A, false. So now let us move to the next question. So the next question is, it is also based on the expectation value and as well as the commutation relation. So in any point of time, if you don't know what will be the expression for commutation relation, then what you can do is just to find out immediately. Like J plus U, the basic expression you know, J plus is Jx plus Ijy and J minus is Jx minus Ijy, and the Jx Jy commutation relation, you know, it is IH cot Jz. So using all this expression, you can easily find out what is the commutation relation for J plus and J bar. So you don't have to remember all the commutation relation. You just have to remember the basic one, so that you can find out what will be the commutation for the other expression. So J plus J minus, if you don't know, then you can find out this way, is Jx minus Ijy. Now use the properties of commutation relation, then you will get it is Jx will be 0, Jx with Ijy will be non-zero, so it will be I times Jx Jy. Now Jx would be non-zero, so I times Jx, and the last term would be 0. So this one you know already know, it is IH cot minus IH cot, no, it is plus IH cot Zz, and this will be minus IH cot Zz. So that means this is 2 H cot Zz. So this is how you can immediately calculate the commutation relation for J plus and J minus or any other expression if you already know the basic commutation relation. So now we know what is the commutation relation for J plus and J minus. Now we can easily find out the value for this expression. One zero. So this is nothing but 1 0 2H cot ZZ 1 0. So now ZZ will act on M. So this is J and this is M. So M is 0. So that means it will give 0 H cot. So the answer would be 0. So that means the expectation of this commutation relation would be 0. Answer would be D.
Ma'am, what if there is z square 1 0 and then commutator of z square and z
Okay.
jz?
Square, how you can solve it is you know the properties of commutation relation A, B, C. So for square, A equal to B, right? It is A square.
Yes, ma'am.
So that means if it is this one, you know, it is ABC plus ACB. So if A equal to B, you will get AC plus ACA. This one, you know, you can just
Sir.
put the expression and you can find out. So that's why I'm telling, just remember the basic properties of commutation relation and the basic commutation relation like Jx, Jy, Jy, Zz. This expression, you just have to remember that. And if you know already that commutation relation, then you can easily find out what will be the expression for other commutation relation. So you don't have to remember all the commutation relation value. You just have to remember only those that is essential. Okay. So let us move to the next question. So the next question is the vector J gives the sum of angular momentum J1 and J2. It is given J equal to J1 plus J2. Here J1 and J2, they correspond to two different particles. Now it is asking about prove that even in this case, the basic commutation relation valid. Like for let's say for a one particle system, you have Jx, Jy equal to IH cot Jz, Jy, Zz will be IH cot Jx and Jz, Jx is IH cot Jy. So this is for one particle. Now if you have two particles, which have one have angular momentum J1 and other one is J2. So even in that system, two particle system, this commutation relation is also valid. Let us prove that. So given J is J1 plus J2. So that means Jx would be J1x plus J2x. You can separate out the individual component of the orbital angular momentum. It would be J2y and Jz would be J1z plus J2z. Now, if you want to, we want to find out what is the relation for Jx and Jy in this two particle system. So you just have to put the expression for Jx and Jy. So Jx is J1x plus J2x. This one is J1y plus J2y. So that means now you just have to use the properties of commutation relation. J1x, J1y. This one with this, and this one with second term. J1x plus J2y. Now we have another expression for J2x plus J2x J1y plus J2x J2y. Now this J1 and J2, they are correspond to two different particles. So that means if you That means this commutation relation J1x with J2y, this is 0 because there are two different particles, they are in different dimension, so they commute with each other. Now, similarly, J2x with J1y would be 0 because they correspond to different particles. If they are for same particle, then it's not 0. Like the first one, this one would be, it is J1x and J1y, so you will get IH got J1z. And this one, you got IH got J2z. So the expression would be IH got J1z plus J2z. So this one is nothing but Jz, right? Using this expression, Jz is J1z plus J2z. So that means it is nothing but Jz. So that means Jx and Jy commutation relation in a two-particle system is IH got Jz. So the basic commutation relation, it will hold even in the two-particle system, or in many-particle system also you will get the same expression. So this is for Jx and Jy. So you can, by following the same process, you can easily get the commutation relation for Jy, You will got it is IH got Jx, and for Jz and Jx, you will got IH got J1. So this two, I am leaving this to you to solve because you can easily find out by following the same procedure. Now let us see what is the second part of this question. So second part is each J1 minus J2 is also an angular momentum. So it is asking whether if you take instead of J equal to J1 plus J2, if you take J equal to J1 minus J2, then is this also a angular momentum operator or not? So you know that if a operator is an angular momentum, then they satisfy the commutation relation Jx Jy equal to IH cos Jz. Similarly, Jy Jz equal to IH cos Jx, and Jz Jx is IH cos Jy. So this is the properties that is held by the angular momentum operator. So now let us see if you take J equal to J1 minus J2, if this properties also holds if we take J equal to J1 minus J2. So let's see. So given J equal to J1 minus J2. So that means J1x equal to, not J1x, it is Jx equal to J1x minus J2x. Jy would be equal to J1y minus J2y, and Jz equal to J1z minus J2z. So in this relation, we have the Jx Jy relation like this. So now let us find out what is the commutation relation held by Jx and Jy. So this is, I think you can find out. You just have to use the properties of commutation. So J1x minus J2x, and Jy is J1y minus J2y, Now use the properties of commutation. You will get 4 terms here, J1x, J2y minus J2x, J1y and plus, sorry, there will be no common, plus J2x, J2y. So this is based on we commute term by term. This with this and this with. So now the terms which are J1 and J2, like this one, this is 0 because they correspond to different particles. So this is also 0. So that means the terms that will remain is J1x, J1y plus J2x, J2y. This is, it is IH got J1z. This is IH got J2z. So that means it is IH got J1z plus J2z. But J1z plus J2z, it is not equal to Jz. Because if you know, uh, here I have shown Jz is J1z minus J2z. If you take J equal to J1 minus J2. So that means it is not equal to IH got Jz. So here you can conclude that this operator, if you take J equal to J1 minus J2, then you won't get the commutation relation that is satisfied by orbital angular momentum, this one. So that means this is not a orbital angular momentum operator. So this is how you can verify whether this is a operator is corresponding to the orbital angular momentum or not. So answer will be no. So I think this one is clear to you. Now let us move to the next question. So the next question is, using the values of J plus Jm and J minus Jm, obtain the matrices for Jx and Jy for J equal to half and J equal to 1. So here we have to find out what is the matrix for Jx and Jy when J equal to half and J equal to 1. Let us see what is the matrix expression for J equal to half. So you know that when J equal to half, M is from minus J to plus J in steps of 1. So it will be, the extreme point will be minus half and this is half. So there will be no M value in between because it is in steps of 1. So that means these are the values of M you will get for J equal to half. So now the expression for J plus when it acts on Jm, you need to remember this. It is H got J into J plus 1 minus M into M plus 1. And there will be J delta or delta. The state will be J and M plus 1. This is the expression for J plus. For J minus, it's easy to remember. The M plus 1 will become M minus 1 only. So this is J into J plus 1 minus m into m minus 1 j m minus 1. And if you want to find out what is the matrix corresponding to Jx, so Jx, you know that it is expressed in terms of raising and lowering operator is j plus n plus j minus, and jy is 1 by 2y j plus minus j minus. So that means you need to first calculate what is the matrix for j plus and j minus, and from that, if you add them and divide by 2, then you will get the matrix for Jx. So let us see the matrix for J plus. So the matrix element you can use this expression to find out the matrix element. So for matrix element we take different J and different M. So this is the matrix element for J plus. So this one would be H cut root over of J into J plus 1 minus M into M plus 1. There will be J prime M prime and J M plus 1. So this is nothing but Kronecker delta, delta J prime and delta M prime M plus 1. So J is same, J is half. So you can take it as 1. This term you can take it as 1. Only this term will remain. So that means this matrix element would be H cut root over of J into J plus 1 minus M into M plus 1 delta M prime M plus 1. Okay. So now let us see what are the values of M. M is 0, 1, minus 1, and M prime is also 0, 1, minus 1. So the matrix, you can write it as so let me explicitly write the expression for the matrix element so that you can easily understand. So let us take so M has 3 different value, M prime has 3 different value. So you will get 3 cross 3 matrix. Now you just have to combine different values of M and different values of M prime. So let us take this one is M equal to 1 and M prime equal to 1. So this is J prime are equal, and this one is M prime M equal to M prime equal to 1. So this is 1 J plus J1. Now the next one, what you can do, you take, so here I have taken 1 1. So in the second part, what you can do, you take 1 0. In the third part, 1 minus 1. 1 minute, let me clearly write what I am trying to say. So the matrix element I have constructed like this. So I have taken for the first. So it will be J plus 1 1. This one is J plus 1 2, J plus 1 3, J plus 2 1, J plus 2 2, J plus 2 3, and this is J plus 3 1, J plus 3 2, J plus 3, 3. So now for 1, 1, what I have done, I have taken m equal to 1. So m has 3 different value, 1, 0, minus 1. Similarly, m prime has 3 different value, 1, 0, minus 1. So now I have taken for 1, 1, I have taken m equal to 1. M prime is also equal to 1. For second one, it is m is equal to 1. M prime is 0. Third one is m is 1. M prime is minus 1. So I have kept m constant and varied m prime from 1 to minus 1. Now for the second row, you change the m from 1 to 0 and take m prime as similar to the first row. So m is 0, m prime is 1. This is m is okay. So this I am taking m as 1, so that means this j is 1, not half, right? I have mistakenly wrote. So this is for j1. So let us first calculate for j1. So for j1, m would be 1, 0, minus 1. So this is 0, m prime is 0, and this is m is 0 and m prime is minus 1. Now for this one, it is m is minus 1, m prime is 1, m is minus 1, m prime is 0, m is minus 1, m prime is minus 1. So now let us see what are the values. J plus thing on Jm and J prime m prime is got root over of J into J plus 1 minus m into m plus 1 delta m prime and m plus 1. And due to this Kronecker delta, whenever this m prime is equal to m plus 1, only in that case the values are non-zero. So that means you just have to check whether in which case this is and this is 0. So that means only, let me see where it is non-zero. Non-zero. So this term would be also 0. This will be 0. M prime minus 1 and this m plus 1 will become 0. So this means this is non-zero. And this one m plus 1 is 0. That means this will be 0. And here m plus 1 is 1. This is also 0. I think this one would be non-zero. So this is non-zero. Only these two terms are non-zero. So now let us see what are their values. So that means j plus is 0, 0, 0. And this one is m is 0 and m prime is 1. So m is 0 means this term will become 0 and j is 1. So that means you will get h cut root 2 here. And this is 0. This one is 0, 0. Here m is minus 1. M is minus 1 and m prime is 0. So this m plus 1 will become 0 here. So that means you will get root 2h cut 0. So this is how you can calculate the matrix for j plus. Okay, so I have taken the combination like I have started from, let's say for find out the matrix element, I have taken 1, 1, 1, 0, 1 minus 1, 2, 1. Sorry. Then I have changed 0, 0, 1, 0, 0, 0 minus 1, then minus 1, 1, minus 1, 0, minus 1, minus 1. So this is how I calculate it, but you can calculate in different way also. So like if instead of starting from 1, you can start from minus 1. So you can take it as 1 minus 1, 1, 0, 1, 1. Then this would be 0 minus 1, 0, 0, 0, 1. Then this is minus 1, minus 1, minus 1, sorry, 0, 0, 0, sorry. So minus 1, 0, minus 1, minus. So you can take this combination also. So it's up to you how you want to find out the expression matrix for J plus. So similarly, what you have to do, you calculate the expression for, so let me show you the PDF file. So this matrix we got. So instead of 1, 1, so I've taken other combination, like I started from 1, 0, minus 1. It's 1, 1, 1, 0, 1 minus 1. So now you will get an expression like this, a matrix like this. So for J minus also, what you have to do, you have to take the matrix element as J prime, M prime. This will be equal to h cut dot over of J into J plus 1 minus M minus 1. So delta J prime, delta M prime, M minus 1. So J prime are same. So what you are left with this one, and J is 1. So that means this is 2 minus M minus 1, delta M prime, M minus. So now what you have to do, you just have to find out the matrix for J minus by taking different combination of M and M prime. Let's start with, so I am writing only, I'm ignoring this J term. So I am taking only M. Let us, it is 1 J minus 1. This is 1 J minus 0. 1 J minus 1. Similarly, I have to change this one. It would be 0, j minus 1, 0, j minus 0, and this is 0, j minus minus 1. And this one is minus 1, j minus 1, minus 1, j minus 0, minus 1, j minus minus 1. Now you see there is a canonical delta, which is delta m prime and minus 1. So that means when m prime is m minus 1, only in that case you will get the non-zero values. In other cases, it will be 0. Now if you see, the diagonal terms would be 0 because for diagonal m is m prime. So this would be 0, this one 0. Diagonal you can easily tell it is 0. For the off diagonal terms, you just have to check one by one. So here m is 0. That means m minus 1 would be minus 1, right? It is 0. And here m is minus 1. So that means m minus 1 would be minus 2. So this is also 0. For this one, m is 1. So m minus 1 would be 0. So that means this is non-zero. This one would be non-zero. And here it is m is minus 1. So you will get m minus 1 as minus 2. This is 0. And here m is 1. For this one, it is m is 1. So m minus 1 would be 0. That means this is also 0. And here m is 0. That means m minus 1 is minus 1. So that means this one is non-zero. So only two terms are non-zero. So that means j minus you get is 0, 0, 0. And this one is 0, j minus 1, 1, 0, 0, 0, minus 1, j minus 0, 0. So for this one, you see m is 1, right? M is 1. So if you put m is 1 here, this one. So this means m into m minus 1 would be 0. So you will get same root 2 h cut here also. You will get root 2 h cut 0, 0, 0, root 2 h cut 0. Okay. Now for j x, what you have to do? You have to take half of j plus j minus. That means half of, let me see, it is plus 0, root 2 h cut 0, 0, 0, root 2 h cut 0, 0, plus half of 0, 0, 0, root 2 h cut. Now if you take the sum, you will get j plus s h cut by root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. This is the value you will get. Think this one. So you will get jx as this. Similarly, for jy, you just have to take the minus of j plus with j minus and multiply 1 by 2y. So if you do it, you will get this one. So this is how you can calculate the matrix for j equal to 1. So now for j equal to half, what you can do, j equal to half, m is either half or minus half. So that means you will get a 2 cross 2 matrix. Okay, you will get a 2 cross 2 matrix, and what you have to do, first we need to find out what is the matrix for j plus and the matrix for j minus. Here for j plus, the different type of combination you can take is m is half, m prime is also half, m is half, m prime is minus half, then m is minus half, m prime is half, and both m and m prime is minus half. So you just need to means follow the same process that I've done for j equal to 1 and find out what is the expression for j plus and jx and jy. So if you do it, let me show you. So this is, I have taken one half half, half minus half, minus half half, and minus half minus. So you will get a matrix like this, and for j minus you will get this matrix. So using this j plus and j minus value, you can easily find out what is the matrix for jx and jy. So I have not completely solved this one. So I think you can follow the same process I have done for j equal to 1. Otherwise, if you want me to solve, then I can solve it. Do you have any doubt in this problem? In any of the steps? Okay. So otherwise, let us move to the next question. So I think this problem is clear to you, right? So instead of any arbitrary j, so here only j half and j equal to 1 was given. So for other value of j, let's say we have j equal to 3 by 2. First, what you have to do, you have to find out what are the values of m for this j, and for matrix, you have to take the different combination of m and m prime, and you have to use the expression for j plus this one, and j minus use this expression and find out what is the matrix for jx and jy. So now let us move to the next question. So the next question is, determine the orbital angular momentum of two electrons when the two electrons are in d orbital. So we have two electrons in d orbital. So it is asking about what is the orbital angular momentum of two electrons in the d orbital. So for different type of orbital, let's say we have s, p, d, f orbital. You know that for s, L is 0, for p, L is 1, for d, L is 2, and for f, L is 3. This one, you know from the definition. So now we have two electron in d orbital. That means for first electron, it is L1 is 2. For the second electron, L2 is 2. So the resultant orbital angular momentum will be L1 plus L2 vector sum, which have values from L1 plus L2 to L1 minus L2. So L1 plus L2 is 4 and L1 minus L2 is 0. So in between we have values in steps of 1. So that means the values are 4, 3, 2, 1, 0. These are the values that we can have for the 2 electrons in d orbital. Now to find out the orbital angular momentum, it is nothing but this root over of L into L plus 1 h cut. So we have values L into L plus 1 h cut. So for different values of L, we have L equal to 4, L equal to 3, L equal to 2, L equal to 1, and L equal to 0. So if you put these values, you will get for 4 it would be 4 into 5. So it would be h cut root over of 20, h cut root over of 12, h cut root over of 6, h cut root over of 2, and this is 0. So these are the possible values of orbital angular momentum that the 2 electron can have in the d orbital. Now for p orbital, for 2 electrons in p orbital, we have L1 is 1, L2 is also 1. So that means the possible values of L would be from L1 plus L2 to L1 minus L2. So L1 plus L2 is 2, L1 minus L2 is 0. So in between we have only one value, which is 1. Now the magnitude of orbital angular momentum would be this would be h cut root over of L into L plus 1. So that means this will give L is 2, L is 1, L is 0. So this will give h cut root over 6, h cut root over 2 and 0. So these are the values for orbital angular momentum. Now for the third part, this one, the electrons are one in p orbital and one in d orbital. So you can follow the same process similar to the first, second. So for the third one, L1 is 1, L2 is 2. So that means the values that L can take is L1 plus L2 to L1 minus L2 means 2 plus 1 to 2 minus 1. This is 3, this is 1. So in between we'll have one value which is 2. So now for the magnitude, what you can do is this h cut root over of L into L plus 1. So that means you will again have 3 values. This h cut root over of 12, h cut root over of 4, at 4 it is 6, and this will be h cut root over of 2. So this is how you can calculate the orbital angular momentum for this question. In any of these steps, if you have any doubt, then you can ask me in any time. So If you don't have any doubt, then let us move to the next question. The next question is based on the polymetric. So is given for any vector A so that this condition is always valid. Sigma commutation relation with A dot sigma is 2i A cross sigma. So we need to verify this relation. So sigma, you know, it has three components: sigma x I cap plus sigma y j cap plus sigma z k cap. Similarly, A have three components: ax I cap plus ay j cap plus az k cap. So that means A dot sigma would be ax sigma x plus ay sigma y plus az sigma z. So now let us see the left hand side of this commutation relation. So this is sigma A dot sigma. Sigma, it is sigma x I cap plus sigma y j cap plus sigma z k cap. And this one is ax sigma x, ay sigma y, az sigma z. Now we have to take the commutation relation term by term. For first one, we have three terms. For second one, you also have three terms. The third one also we have three terms. So let us see. The first one is sigma x, ax, sigma x, I cap plus sigma x, ay, sigma y, I cap plus sigma x, az, sigma z, I cap. This is the first one. Similarly, we have another terms for sigma y, ax, sigma x, j cap ay, sigma y, j cap plus sigma y, az, sigma z, j cap. And another term for sigma z, ax, sigma x, k cap plus sigma z, ay, sigma y, k cap plus sigma z, az, sigma z, k cap. Now, if you see A and sigma are compatible with each other, so that means this one you can take A out from this. So this will be Ax, sigma x, sigma x. So let me compile all the terms which have I component, which is component along the x direction. So this one is move this one to here. So this is ay, sigma x, sigma y plus az, sigma x, sigma z, I kept. So I have just taken A from these terms. Similarly, for other one, you can also take it out the A terms. Is Ax for this one, Ax, sigma y, sigma x, plus for this one, Ay, sigma y, plus this one, Az, sigma y, sigma z, j cap, plus here also you can take it out the A's to outside. So this would be Ax, sigma z, sigma x, plus Ay, sigma z, sigma y, plus Az, sigma z, sigma k. So if you see this term, this commutation relation of sigma z with sigma z, so that means this would be 0. Also this one, sigma y with sigma y, this would be 0. And this one, sigma x with sigma x, this is also 0. So what we are left with are these terms. Sigma x with sigma y, you know that sigma x with sigma y is nothing but 2i sigma z. And this one is sigma x commutation relation with sigma z. This is minus 2y sigma y. Here, commutation relation of sigma y with sigma s should be minus 2y sigma z. And the last one is, no, this one is sigma y with sigma z. So it would be 2y sigma z. Similar, this one is 2i sigma y. This minus 2i sigma x. Right? So that means this is nothing but ay. Let me take out this 2y from 2y is common in all, so let me take it out. This is ay with sigma z minus az with sigma y minus sigma z. Okay, there is a item here also. I cap plus sigma az sigma z. So this is not sigma z, right? This one would be sigma x. Sigma x minus this term ax sigma z jk plus ax sigma y minus ay sigma x kk. And this is nothing but, if you see this expression, this is nothing but the call of A with sigma. So if you check, you can easily check this one, I check cap, I cap, j cap, k cap, and if you take ax, ay, az, sigma x, sigma y, sigma z, then the call, this is the call of A with sigma. So what you will get it. Let me get this question here. If you check this call, then it is AY sigma Z minus AZ sigma Y I cap minus AX sigma Z AZ sigma X I cap plus AX sigma Y minus AY sigma X K cap. If you compare this term with this one, you will see they both are equal. If you check the third one, these are equal. Second one, X is also equal. And the first one is also equal to this one. So that means this is equal to 2i call of A with sigma. Okay. So this question was based on the Pauli matrix. So let us move to the next question. So next question is based on the rotational angular momentum. So it is given the rotational part of the Hamiltonian of a diatomic molecule is. So we have a diatomic molecule. This rotation, the rotational part of this Hamiltonian is given by 1 by 2i Lx square plus Ly square plus Lz square by I. So it is given. Here I is the moment of inertia. Now it is asking about what is the energy eigenvalue and eigenfunction of this Hamiltonian. So we know that if Lx, Ly, Lz, if we have orbital angular momentum, then we can have eigenfunction as spherical harmonics. So eigenfunctions are the spherical harmonics, which we represent it by L m. Now to find out the eigenvalue, what you have to do, we have to act this Hamiltonian on this eigenfunction and find out what is the energy eigenvalue, which can be expressed as ELM LM. Right? So now let us see what we can get. So HR is given 1 by 2i Lx square plus Ly square plus Lz square by I. So now you know the eigenvalue for L square and Lz. So here Lx square plus Ly square is given. So what we have to do, we have to express the whole Hamiltonian in terms of the operator, which eigenvalues are known to you. So L square Lz eigenvalue are already known to you. So what you can do is you just have to express this Hamiltonian in terms of L square and Lz. So L square is nothing but Lx square plus Ly square plus Lz square. So Lx square plus Ly square is given. So we just need to add Lz square here. And there will be a term Lz square by 2i. So I have written Lz square by I equal to 2 times half of Lz square by I. So 1 Lz square by 2i I have taken inside this bracket and the other one is outside. So now this whole term is L square This is L square. So we have L square by 2y plus Lz square by 2y. This is depend 1 minute. So I'm again facing the same problem. The tab got disconnected. So let me show you the okay. So let me show you this way. So we were in question this one. So Hamiltonian we got Hamiltonian is given by L square plus Lz square by 2y. So this one we calculated. So now if you add now Hamiltonian on this operator, so L square you know that the eigenvalue is when it acts on Lm, you will get L into L plus 1 h cut square. So when it L square acts on Lm, you will get L into L plus 1 h cut square. And when Lz acts on Lm, you will get m square h cut square. So that means the energy eigenvalue would be this term, which is h cut square by 2y L into L plus 1 plus m square. So I think this question is clear to you. So let us move to the next question. So the next question is based on the hydrogen atom problem. So it is given an electron is in a state described by the wave function psi equal to 1 by root over 4 pi cos theta plus e to the power minus I phi sin theta into r of r. And one condition is given, the integration of r square and mod of r square dr is 1. This is given, and theta and phi are the polar and azimuthal angles. Now they are asking me about what are the possible values of Lz when the hydrogen atom, when the electron is in a state psi. When it is state in psi, then what are the possible values and what is the probability of obtaining these values? And some expressions are also given, like the spherical harmonics for 1,0 state is root over of 3 by 4 pi theta, and 1 plus or minus 1 is also given. So you can use this expression and solve the problem that is given to you. So to find out what is the possible values of Lz, what you have to do, you have to find out what are the values of m that is present in this wave function. So spherical harmonics are given in this problem. So what you have to do, you have to express this psi vector in terms of this spherical harmonics. And if you express it, then you can easily find out what are the values of m, because from the spherical harmonics, the Lm are already mentioned. Okay. So psi is given. Psi is 1 by root over 4 pi cos theta plus 1 by root of 5 e to the power minus I phi sin theta r of phi. So now if you use, if you compare this psi with the terms that is given here, what you can find is the first expression is term cos theta. So you can express it in terms of y10, and the second term is term sin theta and e to power minus I phi. So that means you can express it in terms of y1 plus or minus 1. So in the second line, I have just multiplied one constant term to make it equal to this spherical harmonics. So if you multiply constant term 1 by root 3 in the first term, you will get the expression like this, and multiply root over 2 by 3, then you will get the spherical harmonics y1 minus 1. So if you see that in this expression, the m values are either 0 and minus 1, right? So here the 0 is present here and there is a minus 1. So that means the possible values of Lz are 0 and minus h cut. Now to find out the probability, what is the probability of getting 0 and minus 1 minus h cut in this case? So for that, you first need to check whether the wave function is normalized or not. So first check whether psi is normalized or not. So for that, what you have to do, you have to take the integration of psi square over the whole space. So psi square dv, dv you know in a spherical coordinate it is r square sin theta d theta d phi dr, where r runs from 0 to infinity, theta runs from 0 to pi, and phi runs from 0 to 2 pi. So now use this expression of psi. So find out what is the value of psi square. So psi square it is nothing but 1 by 3 the spherical harmonic square multiplied by r square. So this term, so in the second line you can take the complex conjugate of this spherical harmonics multiplied by r square term. Now what you have to do, you have to just multiply term by term, like this one with this and this one with this. Now the next term, this one with this and this one with this, multiplied by r square. So this line has all the components. So now what you have to do, you have to put the expression for y10, y1 minus 1 in this whole terms. So if you put it, the first term would be equal to 3 by 4 pi cos square theta. The second term will become 2 into 3 by sin square theta. And for this, for third and fourth term, you will get this term, which is 3 by 4 pi cos theta sin theta into e to power minus I phi and e to power I phi. Multiplied by r square. So now if you see these two terms, it is called, there is a common term which is 3 by 4 pi. So and cos square theta plus sin square theta, it is nothing but 1. And for the third term, for the second term, you will get e to power I phi and e to power plus minus I phi by 2. So now what you have to do, you multiply it 2 here and divided by 2 here. So this, let me use a different color. So this 2 sin theta cos theta, it is nothing but sin 2 theta. And this one is cos phi, right? So just put the expression, then you will get the expression for psi square is this 1 by 4 pi 1 plus sin 2 theta cos phi r square. So now you have to put 2 in the integral form. If you put it and separate out the individual term, like separate the r term, theta term and phi term, then we will see that So the first one, let's see, the first one is R term, the second term is theta terms, and the third one is both theta and phi term. Both are present. For this one, what you have to do for the third term, you just have to solve for phi term, then by taking theta as a constant, then you can integrate this theta term in the this theta term. So let's see whether this one, what is the value for this integral. So here there is one, this one is 1 plus sine 2 theta plus cos phi. So 1 d phi will give 2 pi. Now for the second one, this is sine 2 theta cos phi. You will get second term, we are taking sine theta is a constant. So sine 2 theta is remains constant only. Integration of cos phi will be there. So integration of cos phi is nothing but sine phi, right? So sin phi, if you take the integration from 0 to 2 pi, it will give the value 0. So that means the third term will give 2 pi. Okay. So you will get a value 2 pi here. Now 2 pi, you got the third term. The first term is 1. It is already given in the question. If you see the question, this r square and capital R square is 1. It is already given. It's already given in the question. Only the term that will remain is sine theta d theta integration, which is nothing but the integration of cos phi. So the 2 pi you got from the third integration. There is 1 by 2 pi here and the integration of sine theta d theta. So if you integrate it, you will get a value of 1. So that means the wave function is normalized here. So if a wave function is normalized, then the probability, in that case, the probability you can write it as a square of this coefficient. So psi is already given. Psi is 1 by root 3. Y10 plus root 2 y1 minus 1 into r of r. And psi is normalized. That means the probability of getting 0 is the square of this coefficient, which is 1 by 3. And the probability of getting minus h cot is root over of 2 by 3 square. So that means you will get the probability 2 by 3. So this is how you can solve this problem. So what you have to do if this type of question is given and the expression for spherical harmonics is also given. So you first need to express the psi in terms of the spherical harmonics. From the spherical harmonics, you can get the value of m, possible values of m, and from that you can get the probability. Okay. So now let us move to the next problem. So the next problem is based on Pauli matrix also. So let me read out the question for you. An operator P describing the interaction of two spin-half particles is P equal to A plus B sigma 1 sigma 2. So P is given where A, B are constant, and with sigma 1 and sigma 2 are the Pauli matrices of the two spins. The total spin angular momentum is equal to S1 plus S2, which is h cot by 2 sigma 1 plus sigma 2. Now it is asking, can we measure P, S square and SS simultaneously? So if we have this kind of system where the P operator is given by A plus B sigma 1 sigma 2 and S is given by cot by 2 sigma 1 plus sigma 2, then can we measure P, S square and SS simultaneously or not? So for that, for simultaneous measurement, the concept is like they should commute with each other. If they commute, then we can measure them simultaneously. So for simultaneous measurement, the commutation relation of P with S square, P with SZ, and S square with SZ should be 0. But if you see S square and SZ commutation relation, it is 0 by definition, right? S square, SZ commute with each other, and only we need to verify whether P commute with S square or P commute with SZ or not. So now let us express the P in terms of the operator whose eigenvalues are known to us. Like sigma 1, sigma P is given by A plus B, sigma 1 dot sigma 2. We don't know the eigenvalue for sigma 1 dot sigma 2. So what you can do, we can express sigma 1 dot sigma 2 in terms of the eigenvalues of operator in terms of the operator whose eigenvalues are known to us. So for that, S is given S equal to S1 plus S2. So that means if you take square of this S square, you will get H got by square by 4 sigma 1 plus sigma 2 into sigma 1 plus sigma 2. So if you multiply it, you will get sigma 1 square plus sigma 2 square plus 2 sigma 1 dot sigma 2. Right? So here you are seeing a dot term sigma 1 dot sigma 2. So if you rearrange this expression, you can easily get the expression for sigma 1 dot sigma 2, which is 2s square by h cot square minus half sigma 1 square plus sigma 2 square. Now, here the sigma 1 and sigma 2, they correspond to the different Pauli matrix for this 2 spin. Okay, they correspond to two different particles. Sigma 1 for first particle, sigma 2 for second particle. So, and you know that for the definition of Pauli matrix, sigma x square plus sigma x square is 1. It is the identity matrix. Sigma y square is also 1. Sigma z square is also 1. And if you take sigma 1 square is for the first particle. So you can write it as sigma x square plus sigma y square plus sigma z square for first particle. So each is identity matrix. So that means sigma 1 square will be 3i. Okay, you will get 3i here. Now for the second one, sigma 2 square, this is also sigma x square plus sigma y square plus sigma z square of second particle. So you will get 3i here also. Now, if you put these values 3i in equation 1, then you got sigma 1 dot sigma 2 is 2s square by h cot square minus 3i. Okay, this is the values. This is the final expression for sigma 1 dot sigma 2. So now what you have to do, you have to put the expression for sigma 1 dot sigma 2 in P operator. So for the first one, we are checking the compatibility between S square and P. So S square is S square only, and P is A plus B sigma 1 dot sigma 2. Now what you have to do, you have to again use the properties of commutation relation, that this would be equal to S square commutation with A plus B times S square commutation relation with sigma 1 dot sigma 2. This first term is 0 because A is a constant. For the second term, what you can do, use the equation 2. Use this. So according to equation 2, sigma 1 dot sigma 2 is nothing but 2s square by h cot square minus 3. Now if you again use the properties like A, properties of commutation relation. So first you need a commutation relation of s square with 2s square by h cot square. And second, you got commutation relation of s square with 3i. So if you check s square commutation with s square is 0 and s square with 3i, it is also 0. So that means the commutation relation of s square with p is 0. Okay. So This means that you can measure P and S square simultaneously. Now, if you for the second commutation relation, that is commutation relation of P with S state, you just use the equation 2, the expression for P, and if you check it, you will see term like S Z with commutation relation with A, and the term like S Z commutation relation with 2s square by h square minus 3i. So the first one is already 0, it is 0, and the first second one also Sz and S square, they commute with each other. That means this first term would be 0, and for the second term it is Sz commutation relation with 3i. So this is also 0. So that means for P Sz or commutation relation, the commutation relation of P with Sz is also 0. So this means that you can measure also P and Sz simultaneously. So all these commutation relation are 0. That means this operator P, S square and Z, you can measure them simultaneously. So if in the question they are asking about the simultaneous measurement, so you need to check whether they commute with each other or not. If they commute, then you can measure them simultaneously. And these all operator will have same eigenvalue, not same eigenvalue, same, you can express them in terms of same eigenvector and you can measure them. But if they don't commute, then you cannot measure them simultaneously. Okay. So let me move to the next question. So next question is also, it is similar to the one question that I've solved before. So it is based on the rotational kinetic energy. So it is given the Hamiltonian, the energy levels of a symmetric top molecule with principal moment of inertia, I1 equal to I2 equal to I, and the third moment of inertia is not equal to the two moment of inertia, I1 and I2. So Hamiltonian, for a general Hamiltonian, you can write it as H equal to half Lx square I1 plus Ly square I2 plus Lz square I3. I1 and I2 are same, so you can add Lx square plus Ly square. And for the third term, I3 is different from I. So similar, in the previous question, I have told you to express the terms in terms of the operator whose eigenvalues are known to you. So you have to express Lx square, Ly square in terms of L square and Lz. Okay, so what I have done, I have added Lz square by I here and I have subtracted one Lz square by I here. Okay, it won't change the expression for Hamiltonian. So, and Lx square plus Ly square plus Lz square is nothing but L square. So you will get a term like L square by 2y plus Lz square by 2, 1 by 3 minus I. Now to find out the energy eigenvalue, what you have to do, you have to act this Hamiltonian in terms of in the eigenket Lm. So if you act this Hamiltonian on eigenket Lm, this L square will give L into L plus 1 h cot square and Lz square will give m square h cot square. Right? So that means we will get the energy eigenvalue is this L into L plus 1 h cot square by 2y plus m square h cot square by 2, 1 by I3 minus 1 by I. So this is the energy eigenvalue for this system. Okay. So let me solve this last question. So let me see how many are left. Okay, let me solve this one. So let me tell you how you can approach this problem. Then we can end this section. So the last question is, for a free electron having magnetic moment mu in an external magnetic field Bz in the z direction in the electron's reference frame, obtain its Hamiltonian. So there is a free electron which have magnetic moment mu, and there is one external magnetic field Bz in the z direction. Now they are asking about the Hamiltonian of the system in the first part, and then in the second part, the question is like this: if another constant magnetic field By is applied in the y direction, then obtain the time rate of change of mu in the Heisenberg picture. Okay, so now initially the particle is in a field which is magnetic field in the z direction. Now in the second part, the field is both in z and y direction, and it is asking about what is the time rate of change of this magnetic moment. So now let us see the first part, the Hamiltonian of the system. So Hamiltonian is nothing but in an external magnetic field, Hamiltonian is given by minus mu dot B. So let us see what is the magnetic moment for this electron. So mu you can express in terms of this, which is minus E by M S. And for a spin-up particle, electron is a spin-up particle. So you can write S as h got by 2 sigma. Okay. So now the final expression for mu would be minus mu B sigma, where mu B is the Bohr magnetism and sigma is the Pauli matrix. Okay. So now you can easily write out the Hamiltonian for this system. Hamiltonian is nothing but minus mu dot B. So, and here it was given the magnetic field is in the direction of Z. So that means the only non-zero term will be minus mu Z Bz. Okay. Mu Z is mu B sigma Z. So Hamiltonian would be mu B sigma Z Bz. Now let us see the second part. So second part, there is another magnetic field By in the y direction. And they are asking about the time rate of change of this magnetic moment in the Heisenberg picture. Let us see what is the Hamiltonian for this system. So Hamiltonian is if you have magnetic field in the z direction as well as in the y direction, then the Hamiltonian you can write it as this expression, which is mu b sigma z bz plus sigma y by. And according to in the Heisenberg picture, the time rate of change of any operator is given by this expression 1 by I h got and commutator of mu with h. Okay, so mu you already know it is mu minus mu b sigma, and h is mu b sigma z bz plus sigma y by. So to solve this one, what you have to do, we have to also you have to use the properties of commutation relation and some basic commutation relation properties, like the commutation relation of with sigma x with sigma y with sigma z, and sigma y with uh, sigma y with sigma z, and sigma x with sigma z. Okay, use this, and you can easily find out what is. You can easily solve this problem. So let me tell you what I have done in this step. So in this step, I have put sigma s, sigma x I k plus sigma y j k plus sigma z k k, and this terms remain same. Now in the second part, I have used the commutation relation term by term and use the properties of this Pauli matrix commutation relation. Okay, so use this and you will get a term like sigma cross product of sigma with B. So now if you use the expression of mu and mu B, then you can easily find out the time rate of change of magnetic moment is given by E by M B cross mu. It is similar to the, I think, third question that I've solved. So let me show you. This one. So it is similar to this question. Okay, you just have to use the properties of Pauli matrix commutation relation and find out the answer. So if you check, then you will get the answer in terms of the cross product of sigma with B. Okay, this is the answer. So now let us stop for today. I think the problems that I have solved today is clear to you. So thank you for joining the section. I hope the problems that I've solved is clear to you. Now let us meet on next Saturday. For now, let us end the section. So everyone,